I can solve every problem in my head. I don't need this pen. This is split array into consecutive subsequence. It's like I literally can't solve a single problem without drawing it out. Which is why so many technical interviews are quite absurd, right? Because they anticipate you to share a Google Doc or something, or some coding environment, and you can't draw anything out, right? Seems like design and being able to formulate your idea in diagrams and pictures and drawings is quite beneficial to your job generally, right? Whiteboarding an issue. Yet so many interviews anticipate and expect that you're just gonna, I don't know, draw the diagrams in your mind. So if you have the opportunity to use a tablet or share a screen or something where you can draw out your ideas, it's really beneficial to you and to the interviewer, because a picture is worth 1,000 words. Okay, so you were given an integer array nums that is sorted in non-decreasing order. Okay. Determine if it is possible to split nums into one or more subsequences such that both of the following conditions are true. Okay, what are the conditions here? A little weird here, right? So we're splitting the array into a bunch of subsequences, but I need to split the array into a bunch of subsequences, meaning that all the elements need to be a part of some subsequence, right? I can't neglect any single element. Each subsequence is a consecutive increasing sequence. Each integer is exactly one more than the previous integer. Okay, so your subsequences is going to be like this increasing system one by one, right? You're not going to have like a subsequence 1, 2, 5, 6, 7. It's going to be 1, 2, 3, 4, 5, 6, 7, or whatever it's going to be, but it's increasing by one within that subsequence. Okay, so that's an interesting condition we need to think about, right? If we have any system like A, B, C, then A equals B minus 1 equals C minus 2, or whatever, right? Something like that. And it's not on screen because I'm an idiot. Okay, I don't know why I did it like this, right? But, everything increasing by 1. All right. All subsequences have a length of 3 or more. Okay, and that's an important condition because, if all the subsequences only had to have a length of 1 or more, well, then every array would be a subsequence because you would just have every element by itself, right? If you put every element by itself, they all have length 1 subsequence, then you return it. You don't need to think about this problem. You just return true. So that's why this condition exists. The 2, why is it 3 and not 2? I don't know. Why is it 3? I'm not sure. You would get rid of that, that kind of like default technical, always true condition if it's 2 or more, but for some reason it's 3. So I don't know. Return true if you can split nums according to the above conditions, or false otherwise. So we're just trying to figure out, can we take this array and split it into subsequences such that there's always a way to build a subsequence where all the subsequences we build are at least of length 3, and when you connect to a previous element, that previous element is one less than the current element. All right, so a subsequence of arrays, an array is formed from the original array by deleting some, can be none of the elements without disturbing the relative positions, right? So we can't reposition this array, which doesn't really matter, right? Because the array is already sorted. So if I was going to connect 3 to something to its left, well, then it has to be 1 less than 3. And since the system is already sorted, the only thing less than 3 is to its left, right? And that'll make sense more in a second. So let's do, sometimes when you're doing these problems, it's important to know which example will give you the best information. And, I've already looked at all these examples, and it's this one here. Right, so this example kind of shows multiple cases, multiple considerations that you have to make while solving this problem. So it's best to probably look at this example and use that as a candidate to try to determine, well, what's the nature of the solution? What's the nature of this problem? What's the nature of the conditions? What's true? What's a given? Etc. So let's go ahead and look at example 2. So in this example, we have, what do we have? We have a life. We have nums. Now I'm going to, like I usually do, is I'm going to represent this array kind of as a graph. I'm going to use vertices and nodes to represent each of the items, because usually, these problems are either dynamic programming or whatever they are. There's a relationship between things, so it can usually be beneficial to model them as graphs. Okay, so we have the following elements. We have 1, we have 2, We have 2 3s, we have 2 4s, and we have 2 5s. Okay. Now, what I'm going to do to specify a subsequence is I'm going to, draw an arrow or an edge between each of the corresponding vertices. Okay. And it just so happens that the solution is, well, 1 can connect to 2, and 2 can connect to 3, and 3 can connect to 4, and 3 can connect to 4, and 4 can connect to 5, and 4 can connect to 5. So in these subsequences here, we have 1, 2, 3, 4, 5. So we have a subsequence 1, 2, 3, 4, 5. And then there's another subsequence 3, 4, 5 here, right? 3, 4, 5. 3, 4, 5. Okay. And you see that here. And you'll also notice that all the elements are being used, right? There's not one single element that's being neglected in this problem, right? You're always going to select at least, every element gets selected only once, and it's a part of some subsequence, right? This one is a part of the subsequence, this 2 is a part of the subsequence, this 3 is a part of the subsequence, this 3 is a part of the subsequence, this 4 is part of this subsequence, this 4 is a part of the subsequence, this 5 is part of the subsequence, and this 5 is part of the subsequence. But there's no double. There's no one element that's in 2 subsequences. There's no one element that's in 0 subsequences. Every element is in 1 subsequence. That's an important part of this problem, and it meets the conditions because, this is length, it's at least length 3, this is at least length 3, and it has the condition also true that every element is 1 more than its previous element, or 1 less than its, next element. So this problem's a bit strange, right? Because it's one of those problems where you can walk through and you're thinking about, well, what connects to what and what are the implications? What can I say is always true? What is always beneficial? What will always lead to the right example, the right answer here? Because we can't just numerate through all possible connections, right? It would take far too long. And when we look at the conditions, it's 10 to the 4, right, for the length of nums. And then this is usually interesting, right? This constraint usually can tell you something about the problem, right? The fact that nums of I is so small, right, in the relative scheme, right? Because sometimes they will say nums of I is, from negative 10 to the 9 to 10 to the 9. But since nums of I is between negative 1,000 and 1,000, right, 10 cubed, that's usually an indicator. Not always, but it's usually an indicator that something to do with the problem is going to be benefited by the fact that this range is so small, right? And then num's length is 10 to the 4. So it can't be n squared, right? Because 10 to the 4 squared would be 10 to the 8. So it's got to be somewhere between n or n log n, right? Our solution has to be that fast to pass. That doesn't mean that that's the most efficient solution, but it has to be at least, at most, n log n, or maybe something a little tweaked higher than that or slower than that, in order for this to pass. But an n squared solution isn't going to work, and definitely anything that's farther exceeds that in terms of runtime complexity is also not going to work. So, we're thinking about this. We're thinking we need something that's like n log n or n, and also that this constraint tells us something about the problem. We're not sure yet, but the fact that this is so constrained is peculiar. Usually, sometimes things can throw you off, but usually the fact that nums of I is so constrained, meaning that the value of all the nums are in such a small range, indicates something about the solution. Okay. So with that said, let's start thinking about what the implications are of the choices that we can make at each step and what the steps are. Okay. Now, naturally, when you're solving this, right, everything to your left, the only things any node can connect to in terms of to its left are the things to its left, right? The only thing 3 can connect to is 2. And since this array is already sorted, 2 is going to be to its left, right? And we have to think about when it's beneficial to connect and when it's not, right? And what you should connect to if you can connect to something, all right? So when we look at 1 here, the first thing we're going to say is, well, 1's all alone, so 1 can't connect to anything, so there's nothing we can really do there. When we look at 2, well, 2 could stay by itself, or it could connect itself to 1, right? So I could connect this, or I could not do it. Now, intuitively, you're probably going to think, well, yeah, I should probably connect it, right? But why is that the case? Well, I'm trying to create subsequences of length at least 3. So if I can connect to somebody, I might as well connect to them, right? If 2 can connect to 1, it's only going to benefit me because I'm trying to create a subsequence. Now you might say, well, what would be a reason why I wouldn't want to connect to this 1, right? Because when I connect to this 1, any subsequent 2 can't connect to this 1, right? Because this 1 is already being used in this subsequence, right? When I attach this, that means there's no additional case where 1 can connect to 2. And this will make more sense in a second. So let me make the same point, but with 3. So when I have 3 here, should I connect 2 to this 3, or should I wait? Right? Because the second I connect this 2 to this 3, I can't do this, right? Because there's the sequence 1, 2, 3, but I can't use the 2 twice, right? So when I connect this 2 to this 3, it's locked. So is there some reason why I wouldn't want to do that and instead do this? Right? Is it better to do this, or is it better to do this? Right? Which one of these cases is better? Well, the thing is, you know, I'm going to connect to something before me because I'm trying to maximize the length, right? So I might as well do it. But is it better to use this 3 or this 3? Well, these 3s are the same. If I took this and I was just like, well, what if I just thought of this 3? Because these 3s are equivalent, right? And I moved it over and then put a red line here. Well, it's the same condition. So connecting to something will only increase the length. And if I don't connect to it because I'm thinking about somebody else, well, that's somebody else that can connect to 2, right? The only other thing that can connect to 3 is another 3. But that 3 is equivalent to this 3, right? Connected to nothing currently. So if I decide to connect here or connect here, it doesn't change it because I could just switch the order of the 3s relative to each other. It doesn't change anything. So I might as well always connect to something if I can connect to something because it's only going to lengthen my score, right? Because the only other thing that can connect to that is another 3, and that 3 is equivalent to me. So that's kind of the point here. So when I see this 3, right, in this condition here, I might as well connect to it, right? Because it's only going to lengthen my score. And any subsequent 3 would just be the same case, you know, swapped. So then now what happens, right, when I look at this 3 is, well, I can't connect it to anything, right? I can't connect this 3 to this 2 because this 2 has already been attached to the 3 over here. Now here's where it gets interesting with this 4. So I guess our first kind of observation, our first point is always connect if you can. Right? If you can connect to something, you might as well connect because you're just trying to lengthen the score. In not connecting, only thing that does is let some further element with the same value connect, but that further element is identical to you, so you might as well be the one who connects. That's the point I'm trying to get at. So always connect if you can. That's kind of our first observation. Now, the second thing we notice is, well, there's this 4 here, right? Now, this 4 has options, okay? This 4 can connect to this 3, or this 4 can connect to this 3. And it's like, well, which one should I connect to? Right, I could connect to this 3 here, because I should always connect to something if I can, and I can connect, or I can connect to this 3 here. Now, I can't connect to both, right, because no one element can be in multiple subsequences, or 0 subsequences. So who am I going to connect to? Am I going to connect to the first 3 or the second 3? Well, which one's better? Well, again, you know, I'm kind of doing some hand-wavy things here. I'm not going to prove anything formally to you, but, you know, I'm trying to create subsequences that are at least of length 3. This 3 over here, he's good, right? This 3 already has 3 people in its subsequence. So why would I connect to him? To make another subsequence of length 4 while my buddy 3 over here is hanging? Right? I can connect to either of these 3s, but this 3 is already in good shape. He's already got 3 people in his row. He's fine. This 3 over here, on the other hand, is all alone and has nobody. So I should probably connect to him. I should probably connect to the 3. If I can connect to somebody, I should probably connect to the person with the least number of connections because that person needs me more than the other person does. Right? So I'm going to connect to this 3 because I need this 3. This 3 needs me more than the other 3 does. Okay? So I guess the thing here is always connect to the shortest chain. And what I mean chain is, right, this is kind of like chained together. Right, now this is kind of one of those problems where, you know, you're kind of convincing yourself through the example. And you know, to be honest, sometimes you can't really know if your intuition is right, right? Because you're not going to write a formal proof usually, unless you're like, you know, really going for a top dog position at like a hedge fund or something. But this is sufficient, right? It's just me kind of just hand-wavily proving to myself that this is probably the case, and I'm going to go through that process when I solve the problem and just hope that it's right, right? And by the end of the interview, if it's right, I look good. If by the end of the interview it's wrong and I look bad, you know, that's just the luck of the game. That's the luck of the draw. That's just how this kind of situation works, right? It's a numbers game. So you kind of have to follow your intuition. If it makes sense to you, then just run with it. And then, you know, the interviewer see your reasoning. Just don't make reasoning that doesn't make any sense at all. But this sort of makes sense, right? The idea that, well, I should always maximize the length. You know, I should always try to connect because it only benefits. And, you know, I should always connect to the person that has the least number of connections because, you know, that person's the most stranded. Those ideas are kind of intuitive. So, you know, run with your gut in many cases and just hope that your intuition is right. But it's not always the case. Okay, so now when I look at this 4, well, the only thing that this 4 can connect to, right, should I always connect if I can, is this 3, right? Because this 3 is no longer at the front of the chain, right? It's not the head of the chain, right? It's already connected to 4, so the only thing I can connect to this 3 to is this 4. All right, now I have this 5 here, and now we're going to deal with a similar problem, right? Because who should I connect to? Well, there's this 4, and it has length 4, or I have this 4, and it has length 2. Well, this is I should always connect to the shortest chain, so this 4 here. So this 4 here I connect to. Now look at this 5. This 5 can connect to only this 4. So I connect them together. And look at that. We have the same exact example. All right, we have these things connected. And we have these things connected. All right. Now I'm going to do that in a different color because I'm all about the thumbnail. Baby. Okay, so this is something that works using this example. Now, can we use this same idea to find something that doesn't work, right? And will that be sufficient for us to prove that, you know, this whole process makes sense? Okay. So let's do an example where we can't find a solution. All right. So another example is 1, 2, 3, 4, 4, 5. Okay. 1, 2, 3, 4, 4, 5. All right, so let's follow these same 2 kind of pillars of truth, which are, you know, always connect if you can and always connect to the shortest chain. So 2 will connect to 1, 3 will connect to 2, 4 will connect to 3, 4 has to be by itself because there's nothing to connect to, and then 5 connects to 4. This doesn't work because although everything connects to something, this needs to have at least length 3. So this is why this example is bad, right? So this is bad here. So this one's good, but this one is bad. All right. Okay, so we have our intuition about like how we're going to connect things, but we still haven't determined how we're going to use data structures and algorithms, right? How we're going to programmatically do this process, right? Because when I looked at each of these nodes, I just said, all right, I just need to look at a 3 to my left and connect to it, and I should connect to the shortest one, right? So really succinctly what we're trying to do is always connect. We're going to connect X to the shortest chain X minus 1. Always. Right, we always connect X to the shortest chain X minus 1. It's always our purpose here. Right? So when I have a 4, right, for example, when I have this 4 here, I want to connect 4 to the shortest chain with 4 minus 1. X minus 1 as head. Head meaning the end of the chain that I'm connecting to. Right? So when I have a 4, I want to connect 4 to the shortest chain 3 with as the head, right? So I connect this 4 to the shortest chain ending in 3, which is this 3 here. Right? So let's say that H, let's define a new thing. Let's call this thing H of X always equals the shortest chain ending in X. Okay? So at any example, right, I say H of 1 is just 1 itself. So this is 1. And then h of 2 is the shortest chain ending in x. Well, h of 2 will just be 1 plus h of 1, right? H of 3 will be 1 plus h of 2. This will be 1 plus h of 2. This will be, you know, so on and so forth, right? Because h of 1 will be 1. H of 2 will be equal to 2. It's unfortunate. Now, I'm saying this is 2 because this is 1 plus h of 1, right? 1 plus h of 2, so on and so forth, right? The shortest chain ending in x is 1 plus the shortest chain ending in the previous value, right? So h of x are like kind of recurrence relationship, although this is not exactly dynamic programming. H of x equals 1 plus the shortest chain ending in the previous thing, right? And that'll give me what I want, right? I want to create a head ending at x to the shortest chain x minus 1 is head. So I'm going to connect, so I'm going to create, you know, equivalent way of saying this is I'm going to create h of x, which is going to be connected to the shortest chain, so it's going to increase the head of x equaling the previous element minus 1 plus 1. So what I'm basically saying here is if I want to connect a 4, right, h of 4, I'm going to connect myself to a 3, right? So when I create h of 4, I'm going to connect myself to a 3 and create the shortest head ending at 4. So then whatever h of 3 is, whatever the shortest head is ending at 3, I'm going to connect myself to that, and so on and so forth, right? So we need a data structure that can give us the shortest chain ending at any value. Now, what's difficult about this data structure when you think about it is, well, you know, when you connect something, it's no longer a head, right? When I connect 4 to the shortest chain ending at 3, 3 is no longer a head here, right? So maybe we can learn this from an example, but let's say we have this H array for each of the values, so 1, 2, 3, 4, 5. So let's move this down. Okay, so what I'm going to do here is create this H array where it has the shortest value for each thing, right? Well, the shortest for everything is 0 at the beginning, right? So this is saying h of 1, h of 2, h of 3, right? Here, well, at this point we have, so should I do it after the point? So after this, h of 1 will be 1. Here I can connect h of 2 to be 2, 0, 0, 0. But what you'll notice is now, at this point, there is nothing with the head ending in 1. Oh, man. It's so funny how you can understand something and you start explaining it and you can't find the right way of articulating your point. All right. But, you know, at this point, there is no subsequence. There is no subsequence. There is no chain ending at 1, right? Because I took that 1 and connected it to 2. So this becomes 0. Right? The 1 gets removed. Now here, ending at 3, again, it's the same thing, right? I take the 2 and I connect to it, so now there is no head ending at 2. It only ends at 3. And then this is where it gets interesting, right? So when I connect 3 to 1 plus h of 2, well, now h of 2 is 0 because I took that head, the shortest chain ending in 2, and I connected it to a 3. So now there is no longer that head 2, right? Because I connected it to something. But now we kind of have multiple cases here, right? Because, well, when I have this 3 here and I add it, you know, I could say, well, the shortest chain is 1, ending at 3, right? It's just this 3 itself. But also, you know, once I connect, here's where it gets weird, right? When I connect this 3 to a 4, I'm going to have a chain of length 4 here. But that chain of length 3 is still here, right? At this point, this is not 0. Because at this point in the system, there's still this 3 here that's not connected to, right? At this instance, before I connect this 3 to this 4, there's still this 3 here alone, but this is saying the longest head at 3 is 0. Well, that's because I can't replace this with 1, right? I need to keep track of all the heads that end in 3, right? I need to keep track of everything that ends in a value, right? This head needs to keep track of everything that ends in a value, because once I replace it, right? So we'll start this problem again from this point forward to make this point, okay? So at this point, it looks like this, right? I have a head ending in 3 with length 3, and then at this point, I have a head ending in 3 with length 1. But there's really multiple things ending in 3. The shortest one is 1, but I need to somehow keep track of the fact that there's also this other 3 that's head length is length 3. 3, 3, 3, 3, 3, 3, 1. 3, 1, 2, 3, 2, 4, 6, 7, 8, 9, 10, 24. So when I get to this 4 is going to connect to the shortest 3, which is this one, right? So when it connects to this head, which has length 1, this occurs, and it becomes length 2, and this 3 goes away. So you might be like, okay, this 3 goes away, so this becomes 0. But obviously that's not true, right? Because the shortest head ending at 3 is this one over here. Don't forget about this guy. This value should be 3. Right? So how are we going to encapsulate that into the system? Well, instead of making this 1, we should make this 1, 3. Right? So the shortest is head at 3 is this 1. And then when I use this 1, right, when I decide to use this 1, so every time I use this value, right, and then I use this 1 here, what do we have remaining? We have just the 3 remaining. Right, so I need to keep track of all the things that I'm adding. I can't just remove and replace. I have to keep track of it, because once I remove the smallest head, right, just because I found a new head that ends in 3, that doesn't mean that old one is no longer important. At some point, when I use this shortest head ending at 3, that previous one will become the shortest one. Okay, so when I add 4, so what is 4 going to connect to? Well, 4 will connect to the shortest 3, which is this 3 here. So I'm going to end up using that 3. But now there's 2 things ending in 4. Right? There's something of length 2 and there's something of length 4. Right? So there's something of length 2 now and something of length 4. Now there is no more 3s. And that corresponds to me connecting this 3 to this 4 here. All right, let's move this over. Okay, what else is going on here? So now we have 5. So 5 is going to connect to the shortest 4, which is this 4 with length 2, right, which corresponds to this length here. So then we're going to have 1, 2, 3. We're going to add 1 to that to make this 3, and there's still this 4 there. And I definitely messed something up here. Was there not 2 5s? Oh, there's 2 5s. Okay, well, that's fine. Right, because what I'll do instead is connect myself to, sorry, I got distracted there. So when I connect my 5, the longest thing to connect to is this 4. So now there's going to be, this is going to go away. And then this will become 3, 4, and this will become 0, 0, 0, 0. So there's 2 things ending in 5, you know, it's just 4 here. And then you have the whole system, right? And then what you can see is this whole system is, well, there's 2 chains. We have a chain of length 3 and a chain of length 4. So it encapsulates everything, and there's no chains less than length 3. So we have captured all chains of length 3, length 4. So what it really comes down to is how are we going to create a data structure where we can keep track of, like, you know, we have h of x, but it needs to be the shortest chain ending in x, but it also needs to capture all the chains and always have the shortest chain be at the front, right? So how can we basically create something where the top is always the smallest? And the way we do that is priority queue. Okay? So what we're going to do is we'll create a priority queue that'll keep track of this, right? Because we'll add this to the priority core, add this to the priority queue, add this to the priority queue, add one to the priority queue that moves one to the front. We remove the top thing from the priority queue. We add this to the priority queue. We remove the top from the priority queue. We add this, et cetera, et cetera. Okay? So maybe when I write the code, it'll make a little bit more sense. Okay, so let's say our head is a default dict, and we're going to use this for a priority queue. All right? And then what we'll do is we'll look at all the nums and numbers, right? And what we're trying to do is we're trying to find the shortest solution, right? We just said that h of num always equals 1 plus h of num minus 1, right? But since we're using a priority queue, what we want to do is we want to pop. What do we want to do? We want to make this situation the case, but we have to understand that we're using priority queues here, right? So we're going to push to h of num. And what are we going to push to h of num? We're going to push popping the smallest thing and I'm doing the same thing here. I'm just doing it knowing that I'm using priority queues. So since I'm using priority queues, I want the smallest thing from h of num minus 1, and I want to push that to h of num. So that's basically the same thing, right? So I'm saying pushing to h of num, the smallest thing at h of num minus 1. Right, so this is just another way of stating that using priority queues. And then we just want to return, we want to make sure that all of our sequences have linked at least 3. Okay, so we want to return all chain lengths, I guess, equals 0, or chain lengths greater than or equal to 3, because it could be 0 if it's stuck here. Later, greater or equal than 3. For, we'll do all the values in our value arrays, right? For chain length and values. Okay. So let's run that, and let's print out, let's print H when this is done. So this is wrong, so that's good that we should probably print H just to see what's going on here. All right, so does this create the subarray that, or does this create this, little situation that we want here? So when we start, we have 1, 0, 1. I don't like this fact that 0 here is because it's 0 should be null. So let's just make this a list, and then we'll just say, if there is an h of num minus 1, we can attach ourselves to it. We don't need the CL0 anymore. If there isn't an h of 1, then we just say h of num equals num. Wait, 1. Right, because there's one thing. If there is no h of num minus 1. Ugh. It's always this stuff, man. Okay. So in the beginning, right, weird thing about default dicts is when you reference them, if you reference something previously but you don't set it, it'll still create. So don't think about empty stuff here really at the beginning. So at the beginning, there's just 1 of length 1, right? Then there's 2 of length 2, then 3 of length 3. But then once you add this additional 3, there's going to be a 3 with ahead of 3 with length 1 and ahead of length 3 with length 3. And then you take that 3 and attach it to the 4, so you get 2 and 4, right? So you have this 3 to here, and then this 3 to this 4, then the 5 and 3, 5, et cetera, et cetera. Okay. Right, and basically what this is doing here is I'm saying all the subsequences I find, they have to be greater than or equal to 3. Okay, so time and space. So time and space. Tricky. So let's say n is the length of nums. All right. We have to look at all n numbers, right? So I'm going to look at all O of n numbers. And for each n numbers, I'm going to have to push to one of the subsequences and pop from one of the subsequences. And the subsequence could be at length n, right? There's something weird here because there's definitely a shorter, like a more tightly bound constraint here, but it's definitely n log n, right? Because there's weird things happening where we're removing things and then adding them, right? Like this is never the length of the whole array, but technically, I'm trying to think if there's a manner in which all log n elements get added to this heap. No, because you just remove. So I'm going to say n log n. Somebody tell me. This is always what I struggle with. But technically, I think it can never be greater than nums of I size. And that's only 1,000. Right? This is 10 to the 4, 10 to the 4, 10 to the 3. It's pretty much the same. Let's just say n log n. And then for space, there's most at n elements, so there can be only at most n things that we're adding to the system. So O of n. So O of n log n time, O of n space, yada, yada, yada. Let's go. All right, peace out.